to see. Last class, I think we were talking about the matrices, matrix form of symmetry operations. We will use it once we will come back to the matrices once we complete the similar transformation, because we study something called as special matrices, which sometimes we call it as a reducible form. We do some block diagonalization to convert to the irreducible representation. So matrices will be transformed to reducible form to irreducible form by certain techniques. The techniques which you are going to use is called as similarity transformation. So before applying that to the matrices, let's see what is mean by similarity transformation and define what is a class. Okay, so that's the plan today. So similarity transformation. Say you have at least 3 elements in a group, say A, B, and X. Yeah, so you have say A, B, and X, 3 elements in the group. Then say we can write this as B as X inverse of A into X. Okay, so if you perform, so this is called as similarity transformation. Like we are performing similarity transformation of A by element X, which results in B. Okay, so this is called as similarity transformation, and A and B are related by similarity transformation. If A and B are related by similarity transformation, then A and B are called as conjugate elements. Okay, so this A and B are conjugate elements. So I'll repeat again. So ABX are the elements in a group, and then you can write this in this fashion. So say X inverse A into X results in B. Okay, so what we say is B is a similar transformation of A with respect to X. Okay, so B is a similar transformation of A with respect to X. And if that is the case, A and B are called as conjugate elements. Okay, so this is the definition for similar transformation. One example, say find transformation of. I just in short form I write STO. So similar transformation of.
Not visible.
Not visible. Yeah. There's some question.
And now it is okay.
C3, say with respect to one other plane. So sigma B, say triple prime plane. Okay, so triple prime plane in C3B point group. So the question is you want to find out the similar transformation of C3 with respect to sigma B triple prime in C3B point group. That is the case. So what we can do is C3B, you know, it has E, C3, C3, 2, and 3 planes, right? Sigma B prime, sigma B double prime, and sigma B triple prime. This is we are doing this for last couple of classes. Let's take an example for this molecule. So for this point group, ammonia we take H, H, H. I label it as HA, HB, and HC. Okay, so this is a C3 with respect to sigma B triple prime. No, so meaning What we want to do is sigma v triple prime. So we just want to find out C3 uh, triple prime minus 1 into sigma v triple prime equal to what? So that's the question. So the question is, so what is the similar transformation of C3 with respect to sigma v triple prime with respect for the C3v point group? So this is the question. So you have to find out this relation. Okay, so uh, so C3 sigma v. I think we defined a group for like every element have its own inverse, right? So sigma v triple prime is also equivalent to sigma v triple prime its inverse. Okay, so this relation I think you must be knowing. Huh? Every element has its own inverse. E means E inverse is equivalent. Sigma v triple prime means sigma v triple prime inverse is also there. But the C3 is something slightly different. Okay, so we'll come to C3 a little late for inverse of that. But this is nothing but sigma v triple prime is nothing but sigma v triple prime inverse. Both are same. Okay, so with this validity, let's find out what is the right hand side of this equation. Okay, so we have to uh, evaluate this relation. So we generally come from right to left. Okay, so we operate from right to left. That's the usual practice in group theory. Okay, so let's start with sigma v triple prime. So to perform this sigma triple prime, so we generally follow this notation, right? So triple prime is we place a mirror plane on the NHC atom. Okay, so if we do that, this is sigma v triple prime plane. So what happens? So in nitrogen, HC remains as such. Only these two will be interchanging, right? So I just write HA and HC. So this is done. Now let's go to C3. So if you perform a C3, C3 is along this NHN axis. So C3 rotate. So what happens? You rotate it. So C3 is just 120 degrees, you can say. So it's HA comes here, C goes there, and B comes here. So this is C3 we have performed. Again, last one is sigma v triple prime. As I already told you, sigma v triple prime inverse is equal to sigma v triple prime. So I just say sigma v triple prime inverse. It's nothing but the same one. Okay, so so basically we again place a mirror on this side. Okay, so same place NH. So third, rather than we just place a mirror. So what happens? We end up with N H A will be there, H B, H C, and H B you get. Okay, so this is what we get. So by performing sigma v triple prime C3 and sigma v triple prime inverse, which is nothing but sigma v triple prime. So this we can arrange come by what operation? So what? So it is A, B, and C, right? So this is we can come from starting from normal elements 3 by to this by performing C3 2. If you perform C3 2, starting from here, that is so C3 2. Okay, so just rotate C3 two times. So C3 you do it 2 times, and you end up with this structure. You agree? So your question is, what is the net transformation C3 with respect to sigma v triple prime? The answer is C3 2.
Sir,
Yes.
so first we perform the sigma V from the HC hydrogen and then last from the HA.
Okay, so this is labeling. HABC is a labeling. So our assumption is this plane is sigma v triple prime. Okay, and this one is sigma v double prime. NH, which is on this axis is sigma v double prime, and this one is simply sigma v prime. You, after changing rotation or whatever you perform, this is the notation we are following. So left hand side cutting is basically cutting along N and H. From this side is always sigma v triple prime. Okay, so that's why even after this, I think we placed a mirror here, right? So we placed a sigma v plane. So that's why we are cutting here. We are not worried about ABC. Just the ABC is for our understanding, like where the hydrogen atoms are shifting. But triple prime means it's through this side. Double prime is this one, and single prime is this way. Okay, that's the notation.
Sir,
Yes.
sir, you said it is C32. Sir, if we rotate in another direction, it can be C31 also.
C31 concept. Yeah.
Yes, sir. If we rotate it another in anti-clockwise, so
Anti-clockwise. So yeah, it will be equivalent to C3 minus 1. I agree. Both are same. C32 and
okay, sir.
C3 minus 1 are equivalent.
Okay, sir. Thank you.
Yeah. But yeah, so inverse generally don't come as come in the group. Okay, we don't write inverse elements in the group. So that's why we're not taking C3 minus. So that's why it is just considered C32. Okay, so so the similar transformation C3 with respect to sigma v triple prime results in C32, and then C3 and C32 are conjugate elements. Okay, so this is a good example. So C3 and C32 are conjugate elements. Now we'll define what is class. Okay, so now we just saw what is similarity transformation. Now let's study a class. Class is nothing but a complete set of elements which are conjugate to one another. It's called as class. Huh? So you have so many things, right? So say C3B, you have so many elements. The complete set of elements which are conjugate to each other is called as class of a group. Okay, so last class I think we are talking about the group properties of certain of a group. Like there are 4 properties we saw. Now we are going to see properties of class. How do you define a class in a group? Okay, so that's see some with some examples. So class definition is complete set of elements which are conjugate to each other. Is called as a class of a group. It is I mean it could be equal to number of elements of the group, or it could be less than that of. Okay, so there are some 4 properties here also for class or rules of a class. First one is every element of a class is every element is conjugate of itself, because every element is similar transformation of itself with respect to identity. So it's confusing, right? So one is say A, you can write E inverse A.
Your voice is breaking, sir.
So first rule is every element is conjugate of itself. So because we have E in every group, so every element
is breaking.
of itself. Yeah, tell me.
We can't see board also.
You can't, but it is clear for me.
Yes, sir.
Others?
It is clear, sir. It's clear.
That is
Yeah, maybe your internet may be a problem, but I could see clearly in my screen. Okay, so this is first rule is every element is conjugate of itself. because E is present, so A will always give A. If you operate this E inverse A and E. Okay, so this is first rule. Second rule is if A is a conjugate of B and B is a conjugate of, then B will be a conjugate of A. So A we got right. So A is somehow last time I think we got B as X inverse A and X. So this we got no. So we said A and B are conjugate elements. If this is true, the reverse also will be true. So A equal to X inverse B into X. Okay, so meaning if you perform a similar transformation with respect to A, similar transform A with respect to X results in B, and if you perform similar transformation of B with respect to X, it will result in A. Okay, so so if A is a conjugate of B, then B is also conjugate of A. Okay, so this is valid. So B was giving us X inverse A X, and then one can get A equal to X inverse BX. Huh? So you can understand, right? You multiply with the X on left hand side, and the X and X inverse get cancelled. Then you multiply with the X inverse, then other term gets cancelled. So you will get back A. So this is valid. Um, Third is, let's go to third property. If A is a conjugate of B and B is a conjugate of say C, then A, B, C are mutually conjugate. So third rule is if A is conjugate of B, say B is conjugate of C, then A, B, and C are mutually conjugate. Okay, so if you are performing similar transformation of A with respect to some X and giving rise to B, and if you perform similar transformation of B with respect to X and it is giving C, and then A will be the, if you perform similar transformation of A with respect to another element, it will result in C. Okay, that's what it means. So all three are mutually conjugate in a group. So this is I have to give an example. Just all three is mutually conjugate. So last point is so I have to define what is in the order. I think maybe I didn't tell you about this. So order is the number of elements present in the group. Yeah. So in C3V, I'm given a symbol H. Okay. So say in C2V, the order was H equal to 4. Okay. So 4, how we got E C2 sigma V prime and say sigma V double prime, right? So that's 4. And C3V, its order is how much we got? 6, I think, right? So we got E C3 C32 sigma V prime sigma V double prime and sigma V triple prime, right? So we got 3. So the H is 6. The order is 6 in case of C3V. So order is number of elements present in the point group. So fourth point is of the order is of the classes order of all classes will be integral multiple of the order. Okay, I mean the integral factors of order of the group. Um, so order of all classes will be integral multiple. Integral multiple, order of all classes. So in a group there could be two class like that. Okay, so it will be integral multiple. It cannot be in fractions. We'll see some example. Once I explain how do you find out order for say C3b or C2b point group. Okay. Um, so this is the fourth rule of class. So order of all classes is integral multiple. Integral multiple of order. I mean integral multiple of order. Okay? Order of all classes is or all classes will be the integral multiple of order. Okay, so it's something like this. So we'll see some example how it is valid. Okay, so I'll just take an example. Find out class. Okay, so let's do C3B itself. It's a long one, but yes, try for C3B. So you have C3B in this. You have C3, C32, sigma B prime, sigma B double prime, and sigma B triple prime, right? So H is in this case it's 6. So we have to find out how many classes are present. Okay, so for that, let's see what could be the classes. Okay, so E is class by itself. So generally we have E by its own class. To find out the class, we find out that similar transformation. So let's try similar of C3. Okay, so let's try C3 similar transformation. I just call C3 1. So we are going to use C3 twice also. So to find out C3 1, what we do is C3 1 multiplied by E inverse E will be 1. So again, insert in C3 1, right? So let's try the next one. C3 1 and then multiply with C3 1 inverse C3 again. So this is C3 into C3. It will result in C3 into C3. It will go to C3 2. Okay, so C3 1 into minus 1 is C3 minus 1. This will result in what? This is C3 1 itself, right? So if you perform, I'm just doing a similar transformation for all the elements present with respect to C3. Okay, so third is C3 1 and then C3 2 minus 1. Okay, and then this is C3 2. So what will get the third one? We'll perform a similar transformation of C3 1 with respect to C3 2. This will result in E multiplied by C3 2 inverse. So C3 2 inverse is C3, right? So basically it is C3 into E. So again it is C3. So this one let's call it as C3 1. Now we have done with these three. We have done C3 1, we have done C3 2, we have done. Now let's sigma B prime. So we have to find out similar transformation of C3 1 with respect to sigma B prime. And this is sigma B prime of inverse. So this is sigma B prime of inverse is same as sigma B prime. So let's do that later. So right hand side you have to evaluate. So C3 prime and sigma v is what? This will be sigma v. You have to see the group multiplication table. Can you tell me what is these two operations? Sigma v prime and C3 prime. Sigma v prime and C3 prime. C3 1. Huh? So it's a sigma
V triple prime.
triple prime. Huh? Sigma v triple prime. So these two is sigma v triple prime multiplied by again sigma v prime, because both are same, inverse and this one. So next is again you can see the table, group multiplication table, and then answer sigma v triple prime multiplied by sigma v prime. So it is C32. So I get similar transformation of C3 with respect to sigma v prime is C32. Similarly, you can do it for other two. Okay, so sigma v double prime inverse C3 1, and then sigma v double prime. This will be sigma v double prime multiplied by. So let's evaluate this one. Sigma v double prime into C3 1 is sigma v prime. So you get what? Sigma v prime and sigma v double prime is C32. Again, you are getting C32. So last one also, I'll just finish it for completion. It's triple prime minus C3 1.
Sir, only C3 come. Sigma V double prime and sigma V prime C3.
C2, C3?
Yes, sir.
Okay, I'm wrong. So triple prime, I'm just doing it. Sigma v triple prime, I think earlier we did this, I think, right? Sigma v triple prime and sigma v, sigma v triple prime multiplied by C3. So it's sigma v double prime multiplied by sigma v triple prime. This, what will get?
C3.
C3
Yes, sir.
or C32?
Yes, sir.
Okay, so yeah, we just work it out. I get C32, but yeah, check
C3 too, sir.
one says C3.
Sir,
Message,
sigma
it will result in either C3 or C32 only. So it's a class by. So if you perform a similar transformation of rotational group C3 by all the elements, you can see it is just giving either C31 or C32. Okay, so that's a message. So it's a class by class. This is one class. This is one of the class. Similarly, if you perform C32, if you repeat the process, okay, so if you just take C32, an act of E.
Sir,
Yeah,
the last two are C3 2.
yeah, that's what I was writing. My table says both are C32. Somebody said it is C3. Please cross check it. It does, yeah. So it could be the messages. It results in either C3 1 or C3 2. Okay. So if you perform similar transformation of C3, it will result in only rotational symmetry only, C3 or C3 2. And you can perform again, repeat the same thing for C3 2. You take C3 2 here, again perform the whole process for all the elements and see what you are getting. So you will also end up with either C3 1 or C3 2 only. Okay, not sigma or not E. Yeah, so these two will form a class because it results always in either C3 or C3 2. So these two will result in a class. Okay, so E has its own class by itself, and then it's C3 and C32 has one class. And now let's evaluate I think one of it. Okay, sigma v prime, or you can find yourself. You can say, you can prove it also that there is a these three will form another class. Okay, so sigma v prime, sigma v double prime, sigma v triple prime will form another class. Okay, so this is C3 1 and C3 2 forms one class, forms a class, because it will result always in C3 or C3 2, and sigma v prime, sigma v double prime, sigma v prime, triple prime form another class, form a class. Okay, so obviously what I'm saying is you just take sigma v, substitute here. Okay, so now let's say similar transformation of sigma v prime. Okay, so just use this sigma v prime. So you will end up with, yeah, here it is sigma v prime. It's very simple. If you try with sigma v prime, C3 to sigma v prime will be, you can check it, okay? So you have a multiplication table, sigma v C3 and sigma v prime. C3 into sigma v prime will give sigma v double prime multiplied by C3. C3 1 and C3 minus 1 is obviously क्या क्या था? So again C3 minus 1, which is C3 minus 1 is basically equivalent to C3 twice, right? So this can be written as C3 twice. Okay, so I'm just going to write that C3 twice sigma v double prime. So sigma v double prime multiplied by C3 twice. You see the group multiplication table, sigma v double prime and C3 twice. It gives sigma v triple prime. Okay, you started with sigma v prime, did the similar transformation with respect to C3. It results in sigma plane. Okay, so if you repeat this process for all other elements, it will be one of the sigma only. Okay, the message is, this is the message I want to convey. And you perform this again, you can prove it, like show that the sigma plane form a class by itself. You can prove that. Show that planes in ammonia constitute a class. So that three planes in ammonia constitute a class. Okay, so how do you prove it? Like you take three planes, sigma v prime, double prime, triple prime, and then for every element you perform a similar transformation and see what you are getting. So you never get E or you never get C3 or C3 twice. We won't get it. We always end up with sigma planes, either single prime, double prime, or triple prime. So if that happens, then we prove that all these three planes form a class. Okay, so in C3V there are three classes. E is a class by itself, and then C3 is this is one class, this is another class. So there are three classes in C3. Also, now you can find out how many classes present in C2V. Okay, so you can find out. So C2V has what elements? E, C2, sigma V prime, and sigma V double prime, right? So you have four. This one, so you can find out how many are there in that. So how do you do that? You take each element, and then perform similar transformation, and see what you are going to get. Okay.
Sir, could you please repeat the definition of a class one more time?
Class is complete set of elements which are conjugate to each other. It's called as class. So class definition is complete set of elements. I can write it also. Which are conjugate to each other. In a group. So that's the definition of a class.
Sir, so if each element is a conjugate of itself, can't we say that every element will form a class? Why can't we say like that?
Can you please repeat?
Sir, we already found out like every element is a conjugate of itself.
Yes, yeah.
So can't we just say like C3 form a class?
Yes, yeah, okay.
So like can't we say that like C3 itself is a class because it has itself and its conjugate in itself?
C3 C3 is what you're saying is C3 will give rise to, right? This is what you're saying, right? So C3 are conjugate by itself.
So doesn't C3 itself become the complete set of elements which are conjugate to each other? Like because
It has to
C3 and
operate with
C3
other elements also. Complete set. It's a complete set of elements.
The set will be incomplete, no? When we take only C3, the set will be incomplete.
It's incomplete, yes. So that's what I'm saying. You have to contain a complete set. So you have to just not just E, but you have to operate with what are remaining thing.
Okay, sir. Okay.
So other elements are also there, right? So you have to take the complete set and result in conjugates. Result in that conjugate, either C3 or C32. So then these two constitute a class. Okay, not just one element. Here we are taking only one element, but you have to take complete set of elements in the group. In the group, you have 6 elements, right? For C3b. So you have to take all 6 elements and then find out its conjugate. And then see whether they are forming the class or not. Okay, that's what we have just read there.
So can you again define the line you wrote? Order of all classes will be the integral multiple.
Yeah, so
The
last
order
point,
and
so
classes
class in this case
different.
3, huh? At least in C3b, if I'm not wrong, the class, the order is, the order of group is 6, h equal to 6. Yeah, and then here the number of classes are 3. So it's an integral multiple, right? So 2 times of 3 will result in order of the group. So order of all class must be integral factor, or another definition, order of group must be integral multiple of number of elements in the group. Order of a group to be integral multiple of number of elements in the class of the group. Yeah, so you get number of classes here 3, and then it's an integral multiple, right? So 2 times of 3 will result in 6. That's the fourth rule, which we just define. Order of all classes must be integral multiple.
It should be like that. Order of group is integral multiple
Okay,
of a
order of
class.
group. Yeah, maybe I'm wrong. Yeah, order of group should be the integral multiple of classes. Yeah, maybe I just changed the definition. I just interchanged the wording. Maybe order of the order of group to be integral multiple of elements and classes.
Okay, sir.
Okay, maybe I just interchange. You just replace the order of order of group to be internal multiple of number of classes. Okay, so number of classes into internal multiple will result in order of the group. Okay. So a number of classes will be always lower than that of the group. Okay. Order of the group. So you may be wondering why we find out classes. Because if some of you know about the character table, we write the character table, right? If you see the left hand side of the character table, you will have some notations A, B, E, T, like that. So number of that notations, number of rows in that character table will be equal to number of classes in a group. So that's the reason. So we have to find out how many rows are there in a character table. How do you find out? It's based on number of classes. Okay, so you will have you will have 3 classes. One is of A1 type, other is A2 type, third is E type. Okay. So something like this you will find in a character table of. We'll see. We'll arrive at this state. So I think this is E C3 C3 2 sigma V prime, double prime and triple prime, right? So this is what we wrote. I think group will be able to write it and then multiply. Now here it's character table of C3. Here we write this is A1, this is A2, and then E. So these are some spectroscopic notations. We come to this shortly. But just how many rows we write in this character table of C3B depends on number of classes. So C3B just found out there are 3 classes in C3B. So that's the reason we are getting 3 rows. And then we fill the numbers here. Okay, so if you see a group table, group theory book or any quantum chemistry book, having the group theory syllabus, you see just before the index, so you'll find tables of characters, character tables called character table. Okay, I'm just shown only the part of it. That could be more. I mean, that will be another 2 columns. Something like that. You'll find 2 more columns with some fancy letters, X, Y, Z, P, X, P, then R, X, R, Y, Y, Z. We'll see all these things in future classes. But yeah, so how we define these 3 is based on number of classes. Okay, so there are 3 classes in C3B. That's why we wrote 3 rows only. This first row, the second row, and this third row. Okay. So why we write A and why we write E? It depends on the dimension of the matrix. So that's why we introduced something called matrices last class. So here we try to reduce the matrix. Say you have a 6 by 6 matrix. Okay. And then you want to reduce that matrix by certain procedure to shorter form. Say you want to bring it to the one-dimensional matrix. Okay. Meaning you want to just find out only one character only in the matrix. Okay, so say it's 6 by 6, you want to convert to 1 by 1. So how do we do that? By similarity transformation. So if you perform a similarity transformation, the larger matrix reduces to shorter form. The 6 by 6 can reduce to 3 by 3, and then another set can become 2 by 2, and one more can become just 1 by 1. So 6 by 6 matrix can be reduced to a shorter form. If you can bring it down to 1 by 1, that's a one-dimensional representation. If you can only reduce only to 2 by 2 matrix, then it is called two-dimensional representation, given by symbol E. Okay, and if you can reduce only to 3 by 3 matrix, not more than that. So we stop with just 3 by 3. We cannot reduce further. Then that is notation we give T. Okay. So T is in group theory we write T, E like that. But in spectroscopy we write T corresponds to, I think we just saw last time. T we write as T, in spectroscopy notation T2G, right? T2G and EG. And E also we just write in terms of EG. It depends on whether the molecule has I or not. So that will give. So we'll small EG, right? EG. So like this we start writing it. So it's all about the matrix. So we can stop it here. So next class we'll study about the matrices. How a large matrix we reduce it to shorter form. Our ultimate is to bring it to the one dimension. So A's are all one dimensional matrices. Okay, you have only one element in the matrix, so it's a one by one. So if you bring it down to one by one, it's a one dimensional representation. If you can reduce only to 2 by 2, it's called as two-dimensional representation, and then represented by given by a symbol E. And if a larger matrix can bring it down to 3 by 3 matrix, it's called three-dimensional representation, given by symbol T. Okay, so like this we define, and then we write character table, and then we fill these columns with certain characters, and from that we'll find out whether the vibration is the molecule undergoing vibrational mode is IR active or Raman active, or both modes are active. Okay, so like that we just find out. So again, next class we'll go back to the matrix and then perform some similarity transformation of matrix by finding the inverse, and then reduce the matrix size. So we reduce it to maximum possible. So the matrix which can reduce is called as reducible matrices. If you cannot reduce further, then we call it as irreducible matrices. Okay, we just say and then find out what is the dimension of that irreducible matrix, and then give a notation for it. Okay, so today we saw what is called as similarity transformation, and then some of the then define class, and then some of the properties of a class, and we took the example of C3V and worked out how it is coming. And there are 3 classes in C3V. So the next is you find out how many classes present in C2V point group. So C2V has H as H is 4. So you can find out how many classes present in that. Okay, so that's the exercise I give you. Please work it out and tell me on next class. Yeah, so if you have any other questions, you can ask.